The title of this discussion is CFD Surface Integration and Conservation of Energy. CFD tools provide a very nice mechanism to evaluate fluid systems, including the exchanges of energy and the movement of energy. Oftentimes when we run simulations and want to post-process those results, we want to do surface integrals to look at energy levels and temperature levels, and we would expect those surface integrations to report values that follow the conservation of energy. This video will discuss that in detail. My name is Jeff Franklin. I'm the primary author of the commercial package called Azore. This commercial package is specifically designed to address commercial and industrial level fluid flow simulations. If you'd like to know more about that product, please visit the website azorecfd.com. To start this discussion, we'll just start by looking at a single fluid streamline. And here we have a fluid streamline. It's a packet of mass, and we're kind of following it, and then it will pierce an integration plane. And along that path, we can look at the energy level of that mass and the temperature, and the relationship between the energy level and the temperature is through this relationship right over here, where the specific heat of the mass has it lets us know what the thermal capacity of that fluid mass is, and changes in temperature result in changes in its enthalpy, this H value here. So we can see that if there's no energy exchange along that fluid path line, we would not expect the temperature to change as well. If energy exchange happens along that path line, then we would expect that the temperature will change following this relationship. But in this particular case, our integration plane, there's only one fluid path line that crosses over this barrier, and so the energy level and the temperature, they're kind of unique there. But in our CFD simulations, we often have many fluid path lines. And here we have another system where the system that we might be interested in evaluating is basically two packets of mass. And they kind of travel along, and then they eventually will pass the integration plane. And so now we have two enthalpy levels and two temperatures, but if we group this together and we want to evaluate it as one system, we would like to know kind of the equivalent energy level and a representative temperature there. So we need an integration method that allows us to evaluate this system and all of the changes that happen between where this system starts and our integration plane, and give us an average value that represents conservation of energy. So, and just to kind of extend this concept a little bit further, we have three path lines here, and sometimes the path lines that may eventually cross your integration plane, they could have a very different history from one another. And you can kind of see where this one, it is a little bit longer than the rest of these. And in three-dimensional flows, and CFD tools are very good at looking at three-dimensional flows, the fluid path lines can be quite complex when they cross over that before they cross over that barrier, or even how they cross over that barrier. So we need an integration method that can really account for complex histories of fluid streamlines or path lines. So here's another one that is even more complex, this red line. So basically this path line or streamline, it crosses over this barrier 1, 2, 3, 4, 5 times. So we need an integration method that will be able to accommodate that, because that is a situation that really could occur, because in our CFD tools, we can make any plane we want, and we can cut the flow structures in any way we want. But we still would like to be able to evaluate and come up with an average temperature as long as the system that we're evaluating is well defined as it crosses that plane. So the integration method that we will use, here is the algebra of what that really means, or how we're going to do this. And so what we're really going to do is this numerator here really kind of accounts for the energy flow that would cross over our integration plane here. And here, this is a surface integral where we kind of integrate every single path line, and we look at its enthalpy level, and then this density times the velocity times this would be the area. So we kind of have the energy level of the fluid that is actually kind of crossing over that barrier of our integration plane. But there's also another mode in heat transfer problems where actually energy can cross over our barrier due to thermal conductivity. And here, this is the how you account for that where we have our thermal conductivity and then the temperature gradient as it crosses over that barrier. And so this really gives us this is our conservation of energy that crosses over that barrier, but we want to kind of get an average temperature and have an estimate of the average enthalpy there. And so what we'll do is divide that energy, flux by our mass flow. So this denominator here really represents the mass flow of our system that crosses over that barrier. And if we divide our energy level and by the mass flow, we get an average enthalpy. And this is the average enthalpy at that barrier. And so then we can take that average enthalpy and we can look up a temperature that represents that average enthalpy. And that would be our energy conservative temperature. This really stems from how you look at the energy equation. And I've done a previous video where I discussed in detail how the energy equation is treated, especially when you have variable specific heat. And I would encourage you to go and look at that video, and I'll have a link for that down below. So now we kind of know how we want to evaluate our system, but there are kind of maybe some rules that we would like to observe before we use this surface integration method because in CFD tools, we can kind of cut planes that maybe are not necessarily appropriate to do surface integrations because we maybe have cut our system in ways that don't really make sense and don't allow a conservation of energy to be observed. And so here's the first thing. Basically, the basic rule is a system of streamlines must end on opposite sides of the integration plane for a valid energy conservative surface integration to be performed. So you can't basically split your system. And here I have an example where we have a system, and our system is composed of 3 packets of mass. And you'll notice that one of the streamlines does not cross over that barrier. And so this would kind of make this integral right here of this system right here invalid. If we were only looking at these two, this system of just these 2 path lines, then of course it would be valid. But if we want to know the integrated value of this complete system, then this is not appropriate. Here's another example. If the streamline system is made up of multiple streamline systems, each system of streamlines must either all pass through the plane or never pass through the plane. So here we have a system where we have a group of path lines on the left and a group of path lines on the right, and you'll notice that the red ones do not actually cross our surface integration plane, nor do the green ones, yet this blue set of path lines do. So this would be a valid integration plane as long as there was really no energy transfer between the red and the blue and the green and the blue here. So that would be one valid integration plane where not all of the mass actually crosses over the plane. Here is another thing. If the system is made up of multiple streamlines, and each system of streamlines must either all pass through the plane or never pass through the plane. And here we have an example of that, where our red lines are not crossing over the plane, and actually over here, the green lines, they stay on one side, and that can be okay, but they begin and end on one side, but they do cross over, and then there is some energy exchange right here between the green path lines and the red ones here. So this kind of invalidates the ability to fully define what the system is that's crossing this integration plane. It kind of invalidates the ability to use that surface integration method that was talked about before. Here we have, if the streamline system is made up of multiple streamline systems, but they exchange only energy on both sides and they're fully encompassed, you can see right here we have our blue streamlines. They start and all in on either side, so that's good. And we have right here the green ones, they all cross over, but then they all eventually cross back. And here, that since they're kind of enveloped in the blue streamlines, we could see or maybe presume that all of the energy that may have left these green streamlines could enter the blue ones and then actually come across the plane again. So this would allow us to have a valid integration plane. And at least some of the mass must cross. So if you are kind of evaluating a surface integration plane, then with this method, you're assuming that your system, you have some sort of mass crossing over the plane. And here you can see that their mass does cross, but it goes back over. So the net mass flow through this surface is zero. And obviously, since we're normalizing by the total mass flow of our system, if we normalize by zero, it gives us an invalid value there. So we wouldn't want to do that and use this method for that. So to kind of help give us maybe some examples of what we can relate to, here's a reverse flow example case where we're going to look at an air-water vapor injection system. And here's a schematic of that system, where we have over here, we have a velocity of 3 meters per second coming in up here with air at 400 degrees K. And down here, we're going to remove volumetrically at 1 meter per second. And we're really going to kind of use for discussion purposes, we're going to look at this red integration plane right here. And we're going to say, since we're looking at energy transfer, we kind of have to have a reference direction. And we're going to say our reference direction is kind of passing through the plane here. And then we're going to inject in a little bit of steam up here or down here, 2 injector locations. And then all of the mass is going to come out right here. This will be our pressure outlet. And just for this discussion, we're going to assume that there's no energy transfer, so it's simply a mixing problem. So, like the first case we're going to look at, we're just going to assume that both of the injectors are off. And so we just have the air coming in here, and then we have a volumetrically removing mass here off of this plane, and we're going to look at what that flow field looks like. And this is the velocity prediction and the energy predictions here. And so we can do a mass and energy balance here on this system, where we have a certain amount of mass coming in, which is about 0.5 kilogram per second, and we have a certain amount of energy coming in, which is about 54 joules per second. And it comes in at a temperature of 400 degrees. The air mass flow, so we have a certain amount of mass coming out here, which here is our mass flow leaving, which is on the order of 0.18. And we're also removing a certain amount of energy, which is around 18,000 joules per second. And here is our integration plane right here. And so we can look here, we can also come up with the amount of mass coming through, the amount of energy coming through, and the temperature as well. And the temperature, since we only have one, basically system going through here, and it starts at one temperature, there's no energy transfer, it's all at 400 degrees. And then based on energy balance here and here, we can come up and come up with these values, and we can see that the temperature did not change. So this is kind of our basic system, and what we're really interested in is now if we introduce some mass here or here, what happens? How does that change our problem? So let's just look again at if we're doing an integration plane right here, here is our streamline system that starts right over here. And you can see, based on the basic rules that we have, this would be an invalid integration plane. But in this particular case, since there's no energy transfer in our system at all, and there is a net mass flow through this surface, then this actually is a valid integration plane because it's simply a constant value. Now let's look at a little bit more interesting system. Here we're going to inject some steam in on this surface at a high temperature at 1000 degrees K and 0.1 kilograms per second, and let's see how that changes our system. And so you can see over on this side we have no mass of our steam coming in, but we have the same mass flow rate of air coming in here. We have no mass of vapor coming out here and the same mass flow. So like the energy balance, or the energy and mass balance on this side of our system has remained the same. On this side of our system, it has not. We have more mass coming out here, and the temperature leaving is a little bit higher. It will be. So you can see right here, this is the mass fraction of our water vapor coming in. And according to our CFD predictions and our flow structures, none of that steam makes it back to this barrier. So we really have, here we have one system, and then here we have one system. Here is the temperature predictions. And so our energy levels coming in on the left are the same. And along this barrier, they're the same, but our temperature coming out here is, of course, higher because we've introduced more energy right here. So here's our streamlined system. So, you know, in general, we have a split system, and it could be viewed as, you know, from a strict standpoint, an invalid integration plane, but there's really no energy transfer that happens back in this zone, so this integration at this location actually remains valid. But now we have to think about how does our integration plane matter here, because we have two systems. So we can kind of look at this right over here. This is system 1A, where it's kind of a subsystem that crosses this plane. And so now our integration plane over here would remain valid because this system right here and this system combine together and they all cross here. So that makes this a valid integration plane. Now let's look at an even more interesting situation where we're not going to introduce any steam over here, but we're going to introduce some steam over here where we're going to inject it right in here. Same amount of mass that we injected before, same temperature. So let's see what happens here. And so here in this particular case, when we do our mass balances, you can see that some of the velocity structures of what comes out here does actually cross this plane. So here on this side, we have the same, you know, mass flow crossing this barrier, but this barrier, we have a certain amount of vapor that is crossing this barrier and not very much air that's crossing this barrier. And so now, once again, the mass flow that crosses this barrier is a little bit different. We actually have a negative mass flow rate crossing this barrier. And all of our air is actually crossing this barrier. So none of it is getting swept back in here. And then you can see over here that some of the mass, you know, we have more mass going out here, but the mass flow split between this outlet and this outlet are different because of the introduction of this and the different density that passes through here. So our mass flow split has changed in this system, even though we've introduced the mass on one side of this barrier. And you can kind of see the mass fraction field here, where a lot of the steam goes through here, but not all of it. Some of it does make its way over here to the right. So now let's look at our streamlined system. And in this particular case, our streamline system, since there's energy transfer that happens here, this is an invalid integration plane, and it is truly invalid because there's energy transfer here. This system gets split, and some of the mass leaves here, and some of the mass leaves here. And so this would really be an invalid integration plane and not a plane that we would want to use the energy conservative methods. We would have to use, if we really wanted to know some sort of average temperature there, there's really no such thing as an energy conservative temperature. Perhaps we could come up with an average temperature based on other methods like area or mass weighted. Here we go. Let's look at the energy balance predictions here. So we have the same amount of energy coming in here, but you'll notice that the energy going across this plane is actually going in the opposite direction. And here, since this is an invalid integration plane, if we use those techniques, you will notice here that the temperature that we would get is 281 K, which doesn't make physical sense because our system has 400 degrees K and 1000 degrees K. So you would expect, since there's no energy exchange, that our temperature should remain at least between these two values, and clearly it does not. And that's because this is an invalid, and the system that crosses over here is not well defined. So now we really kind of have maybe a better understanding of some of the rules there, but oftentimes I think it's worth discussing the fact that oftentimes when we run a CFD simulation, we might truncate the flow structures. And here, if you kind of imagine we want to run a simulation of this system, but we're going to pick an integration plane, we're going to pick a truncated model where our model is only on the right-hand side, and we're going to start our simulation right here. And perhaps maybe we have some test data here that says what the velocity structure is here, or perhaps this is an outlet boundary condition that we chose, and then it develops these flow structures. Either way, we have, either we're specified a velocity profile here, or this kind of velocity profile structure develops because of an outlet boundary condition that we chose. What would really happen here? And we can see that that is going to give us kind of some strange values. So let's just look here. If we were to do that, we would imagine that we would have kind of our case 2 and case 3, and we can see that we're going to expect different results for these two cases because of our boundary that we chose right here and the flow structures. And you can see the amount of mass that comes out on this side is different. Here, the vapor mass flow rate is 0.1 kilograms per second, but in this particular case, it's about half that because some of the mass that's being injected, even though it would be injected into the subdomain, it's getting sucked out because of the boundary conditions that we may have chosen there. And the same goes with our energy. You'll notice that even though we've put the same amount of energy in on this side of our barrier, the average temperature going out is notably impacted by how the boundary condition we chose right here. So this is an important fact to consider if we actually end up with inflow either defined by us or it develops because of a pressure boundary condition that we chose. So in reverse flow situations, it really becomes dependent on our internal flow structures to the right here. The streamlines become split, even though they may not look like it when we choose our boundary conditions. We are kind of splitting the system, and the system becomes not well defined. And so if we are running simulations, say for instance we're doing design simulations, and so we want to make comparisons between one design simulation and another, we need to kind of be aware of that, and really we shouldn't use and come up with a constant temperature there and look at temperatures that we might have there. To really do a comparative analysis of our systems, we should fall back and really go back to our fundamental boundary condition, which is our energy boundary condition, and we would use temperature distributions right here that give us constant energy. So we want to basically put a constant amount of energy in at this location for whatever choices we may make downstream. And that way we are being consistent about the amount of energy that's being put into our system. So that would be kind of maybe one suggestion to consider when you have inflow on a boundary and you're trying to pick your boundary conditions, yet want to have energy conservative evaluations of temperature distributions that fall downstream of our boundary condition. And of course, the same considerations for our mass fractions fields, if you have a mixture system, should also be exercised. So that really that concludes all of the technical content here. So we really reviewed surface integration methods, and we talked about an integration technique that can be used that really reports temperature values that honor conservation of energy. And we've kind of looked at a number of 2D streamlined systems. We've looked at no heat transfer. We've looked at downstream when we inject and see, and we've looked at how our integration plane can be kind of impacted by different flow structures there. And then we've just briefly discussed about the reverse flow boundary conditions. And if we have those, how we should choose our boundary conditions to really kind of have repeatable values, especially if we're doing comparison-based simulations. If you have more, if you're interested in more content like this, I would encourage you to go over to the YouTube channel for Azore CFD, and you'll find more of these. If you're interested in Azore, this commercial package that really is geared to solving difficult industrial level problems, please go over and visit the website azorecfd.com.